error from yesterday. Let's fix that first. There was one idea about how partial fractions work that I skipped, and that is the for partial fraction decomposition, section 4. In addition to those rules about the factors, the numerator has to be of lower degree than the denominator. So the numerator degree has to be less than the denominator. And I tried to do a partial fraction decomposition on a fraction that looked like this, x squared plus 3 over x squared minus 15x plus 56, I'm pretty sure. And I can't, 56, not 5x. All right. And I did not check that condition before I continued, which meant the values for a and b I found would not work if we tested them, and we never did test them. So what you have to do is, if you have an improper fraction, which is what this is, then you have to do long division. So that means I have to take the x squared minus 15x plus 56 into x squared plus 0x plus 3. When you do polynomial long division, you have to keep track of every power of x, even if it doesn't appear to be there. So then I ask myself, well, how many times does x squared go into x squared? Answer? Once. Yeah. So then I'd say take 1 times this polynomial. So that gives me x squared minus 15x plus 56. And then I have to subtract that whole black line, and subtraction is adding the opposite. So I'm just going to go through here and add the opposite of each of these terms. So I'm going to go through and change their signs. And then I'm going to add coming down. So x squared minus x squared is 0. 0x plus 15x is 15x. And 3 minus 56 is negative 53. So what I've discovered is that this denominator goes into that numerator once, and there is a remainder of 15x minus 53 over my original denominator, x squared minus 15x plus 56. And now I can do partial fractions on that proper rational function, because the degree of the numerator is less than the degree of the denominator. But that has to be true before partial fractions can work. And I don't mind this first part too much, because I love taking the antiderivative of 1. It's quite nice. So we'll continue this problem by doing it correctly. And so now I have to apply partial fractions to this part right there. So keep in mind that 5x minus 53 is really divided by x minus 7 times x minus 8, because that factors, we always have to factor first. Ooh, thank you, it's a 15x, yep. Good job. And now that I have a proper rational function, I can say this is equal to some number a over x minus 7 plus some number b over x minus 8. And I have to identify what the values of a and b are. So the next step is then to multiply both sides by the common denominator. And so all the denominators should cancel. So I'm multiplying everything by x minus 7 times x minus 8. And usually I skip writing that. I just kind of think it. So we have to distribute that to each term here. So on the left side, I'm left with only the numerator, 15x minus 53. The x minus 7 cancels, leaving a times x minus 8. And then x minus 8 cancels, leaving b times x minus 7. And so then it's this thing here. Oops, missed part of it. Get it? I still missed some of it. Oh well. Back to a new screen. We have to figure out what to do with that. Two techniques there. One technique the book says is to multiply everything out on the right and then combine like terms. The other way is to pick convenient values for x. So I did a few examples yesterday. I picked convenient values. I'm going to show the other method today. Most of the time, redistributing on the right, I get ax minus 8a plus bx minus 7b. And then bringing the x terms together and the constant terms together, I get ax plus bx, which factors as a plus b times x. And then I get my negative 8a minus 7b. And the theory goes here that that has to be equal to the 15x minus 53. So then the a plus b has to be the same as 15. And the negative 8a minus 7b has to be the same as negative 53. So I get a system of equations I then have to try and solve. So negative 8a minus 7b equals negative 53. And so any method you want to use to solve that system is one way to go here. So let's see, the bottom one cleans up just a little bit. I could rewrite that as positive 8a plus 7b equals 53. And then I think this lends itself well to a substitution. What do you think? So maybe I'll say a equals 15 minus b when I rewrite that one. And so substituting in, what do we get? We get, switch colors, a, so we get 8 times 15 minus b plus 7b equals 53. And 8 times 15 is what? 120, thank you. 120 minus 8b plus 7b equals 53. Combining like terms, how about negative b, subtracting that 120 to the other side, this gives us negative 67. That sound right? I think so. So it looks like we've got b is 67. And a is 15 minus that. And so it looks like a is negative 52. Okay. Now, just for fun, when I realized I made an error in class, I did that over. So let's see, where's my YouTube page? I put it on there. YouTube, Calculus 2. Is it down here at the bottom, maybe? Partial fractions. Oh, okay, there we go. I put a note down here that I made an error at 6 minutes and 40 seconds in and posted a link to my Google Doc. So let's see. I did the convenient value method where I picked x equal 8 and let's blow that up a little. X equals 8 and x equals 7, and that led me to the same conclusion that b was 67 and a was negative 52. I mentioned earlier that often I find the convenient value method quicker than the method the book shows. So it's up to you which way you want to do it. Oftentimes I'll do it both ways to make sure I'm not screwing up because this is complicated algebra. There's a lot of places to make an error. So usually a couple methods is a good idea. So questions as to where we're at now here? Doing all right? All right, so now it's time to put this all back together. So help me put this back together, please. Our original integral was x squared plus 3 over x squared minus 15x plus 56 dx. And first we did division, and the division let us write it as 1 plus a proper fraction. Based on that proper fraction, we think a is negative 52, is that right? So negative 52 over x minus 7, I think, goes with the a. And then 67, am I on the right track? With x minus 8, did I put those in the right spot? Okay. And now we're ready to find an antiderivative. So we think the antiderivative of 1 is x. Negative 52 is just hanging out, so we'll write negative 52, and then that's going to be times the natural log of the absolute value of x minus 7 plus 67 times the natural log of the absolute value of x minus 8 plus c. And you know, I could bring the 52 and the 67 in as powers and then do a little division, but that looks way uglier than this. I think I'm happy with that right there. Yeah. Yeah, I don't think it's worth cleaning up the algebra on that. And then the only ways to check that this is true are to take the derivative of this thing right here and hope you can clean it up algebraically to give you that back. Other thing I did to check myself was I did that other method and I got the same antiderivative down here when I did that. Another thing I did to check that out, what the heck did I do here? I did some kind of check. What was I thinking? Oh, I know what I did. To check this decomposition right here, I thought the common denominator would be x minus 7 times x minus 8. So then this would be the numerator if you tried to combine all of that stuff together again. And cleaning up that new numerator, it broke back down to x squared plus 3, which is what the original numerator was. So I did algebra on this to make sure I got back to that, is what my check down here is all about. Because I think we can see pretty clearly if we take the derivative of this right here, we will definitely get that right there. And then you have to do algebra to make sure that leads back to this, which is what I've done in green here. Okay, so feel free to play with that some more later. Next, we have a homework question, number 15, is that what you said? And then another note here, and I gotta remember to email everybody. If you do at least half of this assignment, since I forgot to shorten it, we'll call that good. If you wanna do more than half, then I'll throw you a little extra credit. So I'll take a look at that later. So number 15 in the homework is going to be something like, and this is in section 8.4, 9x squared plus 6x plus 9 divided by x cubed minus 1. And so we want to integrate that sucker, find an antiderivative. So first check, since I forgot to mention this last time, is this a proper rational function? Answer is yes, because the degree of the numerator is less than the degree of the denominator. And then I want to make sure the denominator is completely factored. Sometimes it's nice to factor the numerator also to see if anything cancels, because that would be nice. So let's try and clean these guys up. So first thing, the denominator, if you have the difference of two cubes, a cubed minus b cubed, that's going to be equal to a minus b times a squared plus ab plus b squared. Does that look right? I think that's correct. Yeah, pretty sure that's right. I guess I better double check. Difference of cubes. I believe this internet will just give us any answer we want by typing in the right thing. That's the one. And if, oops, sorry, down here. Notice the difference between these two. The sign in the middle is always going to be the sign in the linear term. So a plus is a plus, a minus is a minus. And then otherwise, you want a negative kind of subtraction as soon as possible to make stuff cancel out. So if this was a plus, you'd want the minus to be right there. If this was a minus to start with, stuff's going to cancel. You don't need any more. That's kind of the way I remember that. All right, so algebra is our friend here. So according to that, my denominator, switch back to black, can be rewritten as x minus 1 times x squared plus x plus 1. If I try to factor x squared plus 1 off to the side, 1 only factors as 1 times 1, and 1 plus 1 is 2, not 1, so this does not factor. That is what we call an irreducible quadratic factor. What about our numerator? Let's see, we can pull a 3 out of that, and that gives me 3x squared plus 2x plus 3. And then similar, using the AC method, factor by grouping, 3 times 3 is 9. 9 factors as 1 times 9 or 3 times 3. Since everything is positive here, you must add these factors to get 2. That ain't possible, right? So this doesn't factor either. So nothing is going to cancel here, and now I need to try my partial fractions. Okay, so partial fractions on this one. This is going to be equal to a over x minus 1 plus, since that's an irreducible quadratic, we need a linear factor in the numerator. Oops, and I'm already using a. So we'll do a bx plus c over x squared plus x plus 1. And we just have to come up with the values of a, b, and c. Multiplying by the common denominator being that denominator right there, I get complete cancellation on the left. So we get, I guess I'm going to put that back to the original form up here. Let's undo that. So we're going to call this 9x squared plus 6x plus 9. I don't see the benefit of having that 3 factored out at the moment. And that's going to be equal to a times the other factor, x squared plus x plus 1, and then plus bx plus c. The factor of x squared plus x plus 1 will cancel, leaving the factor of x minus 1 behind. And again, just a reminder, what I'm doing is I'm multiplying both sides of this equation by x minus 1 times x squared plus x plus 1. So I have to multiply that here, I have to multiply that here, and I have to multiply that by there. So that's why on the left side we get full cancellation, and on the right side we get partial cancellation in 2 different places. Okay, so convenient x values here, pretty much the only convenient x value is 1. And then otherwise we could do something like plug in 0 and 2 maybe, or we could try the combining terms approach. So I'm going to do the combining terms approach again, just because I've only done it once so far. Combining terms, I have to multiply out the right side. So that's going to give me an ax squared plus ax plus a. And then multiplying here, that's going to be a plus bx squared minus bx plus cx minus c. Looking for like terms. Let's see, I have a square, x squared here and here. So the coefficients of x squared are a, positive a, and positive b. The coefficients for x, let's see, we've got an a, we've got a negative b, and a positive c. So when I put those guys together, again, there's an a minus b, and a plus c times x. And the constant terms are the only things I haven't highlighted, which are just a plus A minus a C. And so the system that we're going to end up with is where we equate these. So the A plus B, that's going to have to be this 9 here. And the A minus B plus C, that's going to have to be 6. And the A minus C is going to have to be 9. So we have a system that we can try and solve. So let's see if I can get that right on a new page. Help me out. Let's see, I think we have A plus B, there's no C, equals 9. A minus B plus C is 6. Am I doing okay? And then A no B plus C or minus C? Minus C, thank you. Minus C equals 9. And I like to space them out like that, indicating like all the A's line up, all the B's line up, all the C's line up. It makes me feel safe. A little security blanket. So we could either go through solving this with substitutions and eliminations, or we could put it in matrix form and have a matrix calculator do it for us. I'm going to do it both ways just for fun. The matrix version of this, we make what's called an augmented matrix. Augmented matrix is where you take the coefficients of A, B, and C. Matrix usually gets a square bracket. Coefficient of A is 1. Coefficient of B is 1. Coefficient of C is 0. And on the other side, I have a 9. And then I have a 1, negative 1, 1, 6. And a 1, 0, negative 1, 9. And again, lining up the A's, B's, and the C's helps me write the matrix easier. And then I just look for a matrix calculator. Now, I believe I put a link to one different than we used the other day under the resources page. I should put a link to that one we used yesterday. So a friend of mine recommended this to me after class. All right, so I just type in my numbers. So let's see, it was 1 tab 1, oops, 0, oops, shift tab. That was 1 and then a 0. And then a 9. Let me blow this up so you guys can see better. Somehow you have to find a device to type into. And let's see, Wolfram Alpha said it did matrices, but I haven't tried that yet. What was this one? This one was a 1, negative 1, 1, 6. And then a 1, 0, negative 1, 9. Did I get that right? Let's see. Yeah, that looks right. And then I just hit right here, it says reduced row echelon form display. And so I think I just hit go, and it says this was your matrix. And then this is the reduced matrix here. Let's blow that up some more. So it says A should be 8, B should be 1, and C should be negative 1. Anyone get similar results on their tool? You tried the TIs and they worked pretty good? You just did it on paper? Okay. Yeah, so this one didn't look that bad by paper, but some of them, we could have 5 terms, and that's kind of fun, but it's not that fun. So, all right, so I believe that's the answer. Double checking on paper. Let's see what would be easy to do here. I guess just substitution, or like there's a couple of eliminations, but yeah. Yeah, let's do that. So let's see. A equals, or you did a B equals? B equals 9 minus A. And so in that next equation there, I get A minus, we're saying B is 9 minus A, plus C equals 6. Cleaning that up, I get A minus negative A, which is a 2A, minus 9 plus C equals 6. Adding 9 over, 2A plus C equals 15. And then combining that, 2A plus C equals 15 with A minus C equals 9. I can just add those guys. So 3a is equal to 24. So there's the same a equals 8 that other program gave us. Once I have a as 8, then I know b is equal to 9 minus a, which is 1. And c is going to be, let's see, if I bring the c over on this one, c is equal to a minus 9, which is c is negative 1 then. Is that what that program said? 8, 1, negative 1. 8, 1, negative 1. Yep, same thing. All right, and there's my a, b, and c equals. Cool. All right, that's half the battle. So now we get to rewrite this thing. So we had the integral of 9x squared plus 6x plus 9 divided by x cubed minus 1. And we believe that is equal to the integral of 8 over x minus 1 plus x minus 1. B is 1, c is negative 1. Did I get that right? Over x squared plus x plus 1 dx. And now we need to find an antiderivative, so let's do that in parts. Antiderivative for 8 over x minus 1 is 8 times the natural log of the absolute value of x minus 1. And then we have to deal with the integral of x minus 1 over x squared plus x plus 1. What can we do there, do you think? Would a u substitution work? Just note, it's always good to write stuff down. If we let u equal the denominator, maybe x squared plus x plus 1, then du would be 2x plus 1 dx, which isn't quite my numerator, so that's out, darn. What else could I do here? Trig substitution, maybe? Integration by parts. Another option is to break this into two integrals. Because we have a minus in the numerator, we could say this is the integral of x over x squared plus, oops, there's not a 2 there, x plus 1 plus, or I guess that's a minus, minus the integral of 1 over x squared plus x plus 1. So that's another option, breaking it into two parts. I think I'm going to like that option there. So let's see, this sucker right here, what could I do with that? I don't have a dx around, which is kind of a problem.
What if you treat them as negative?
Treat what?
So treat them as inverses?
As
so
inverses.
Like -2.
Say it again, Darren.
So treat it like so it's like x to the -2 plus x to the -1.
Oh, we can't do that individually because this is one big chunk here. So the best we can do on that right there is say that's x squared plus x plus 1 to the power -1. But exponents do not distribute over addition. That's not a proper rule. So, and here I have a function within a function, which means I would need a u substitution, but I don't have du outside of that. But I did mention a trick about that the other day. Does anybody remember what I played around with in class yesterday? completing the square. So we could complete the square on this sucker right here. We did one like that in class the other day. So let me pull some of this out of the way. So completing the square, let's do that on a new page and come back. X squared plus x, was it plus 1? Yeah. So what we do is to complete the square, you consider the middle coefficient. That's what you call b, it's 1. And you take half of that. What's b over 2? Well, that's 1/2. And then you square that, which should be 1/4 for us. So if this were x squared plus x plus 1/4, then this would be a perfect square. That would be the square of x plus 1/2. Right? Because this would give you a 1/2 x plus a 1/2 x, which is the 1x, and a 1/2 plus a 1/2 is a 1/2 times a 1/2 is a 1/4. Now, we still have this 1 hanging out here, so that's still chilling out. And I can't just add a 4th in, right? I've totally changed it. So to adjust that, we have to subtract that same 1/4 to keep things legal. So I'm adding a 4th here and I'm subtracting it there, which keeps me balanced. So that means this outside term over here is 1 minus a 4th, which is plus 3/4, right? Okay, why does that matter? Well, you could consider this a u squared plus an a squared in the denominator, right? Do we have an integral formula for things that look like that? Anybody remember which one it is? I think it's the inverse tangent. What do you guys think? Inverse tangent? So let's just double check just to make sure. So everyone was working on that cheat sheet the other day. So let's see. Derivative formulas backwards is kind of similar. So if I look here at the derivative of the inverse tangent, I should see it's 1 plus x squared. Now the book in the beginning of chapter 8 threw an a in there, and what you end up in the formula is that the antiderivative of something like this is the arctangent of x, or sorry, u over a, and then you get your plus c. Now, in this case, if u is equal to x plus 1/2, I guess I don't need parentheses on that, then du would be what? Dx, so there's no constants we're losing, so it's pretty straightforward. So then for us, our antiderivative would be the tangent inverse of x plus 1/2 over 3/4 would be our antiderivative for that sucker right there. Okay, we still have that other one to deal with, so I got to head back to this page over here. So we just found this antiderivative right here. So we're going to have a minus the inverse tangent of x plus 1/2, and we could clean that up a little bit algebraically, over 3/4. And eventually we're going to have a plus c. All right, we still have to figure out what to do with this puppy right there. What are we going to do with that one? Let's see, does it help to rewrite that like we rewrote the other one? What if I say that is the integral of x over x plus 1/2 squared, was it plus 3/4? Is that what we had? Ooh, I made a mistake. Darn it, what did I make a mistake of? That's not supposed to be a 3/4, is it? Yeah, that's a squared. I want a. Whoops. Where's that page over here? Yeah, so this says, let's switch to red, a squared is 3/4. So a is going to be the square root of 3/4. which I could say is the square root of 3 over 4, over 2, oops. So fixing this, we get the square root of 3 over 2 there. Okay, so fix that. All right, back here. 3/4 dx.
TV on row.
What do you
Please.
think? Yep. Is that in there too? Did I miss that? Let's see, where's our book? Documents. Math, where's math? There it is. 252. Textbook. Chapter 8. And blow that up. Oh, yes, there is going to be a 1 over a in there too. Thank you, I missed that. So here, that should be a 1 over a. And so that will be 2 over square root of 3. Thanks. So anybody have any thoughts about this one we still need to figure out? I think a U substitution might work. So my guesses are U substitution or, let's see, I don't think integration by parts will work, but it might, or trig substitution might work here. So let's see, if I were to do a U substitution there, what might I do? I'm not sure if that helps. If we let U equal that whole denominator, we already tried that there. I don't have, that mixes up the X's and the U's.
What happens if we distribute that?
Distribute.
Yeah, x plus 1/2.
If we multiply
And
all this out, we'll get that back. Because we completed the square on this to get that. I'm thinking trig substitution, so let's try that. New page. So we are trying to deal with x over, and I'm going to keep it in the completed square form, x plus 1/2 squared plus, and I'm going to write this as square root of 3 over 2 squared, so that it's of the form u squared plus a squared. And so a triangle for that, let's see if this helps, is going to look like, let's see, that would put my u over here. And so my square root of 3 over 2 goes over here. And this side is my square root of x plus 1/2 squared plus square root of 3 over 2 squared. And then the tangent is opposite over adjacent, so then x plus 1/2 is equal to square root of 3 over 2 times the tangent of theta. And then this side over here is going to be, the secant would be the square root over hypotenuse over adjacent. So we'll get the square root is equal to square root of 3 over 2 times the secant of theta. And then from this line here, we can get our dx. So differentiating this side, derivative of 1/2 goes away, so we just get dx equals square root of 3 over 2. Derivative tangent is the secant squared of theta d theta. Now up here we have that integral with respect to x, so what are we trading out? We've got, let's rewrite it in blue. The denominator is the square of the square root, so I'm going to have to square this side right here to get rid of the root because we don't have it there. So square root of the constant is 3/4 secant squared of theta. And then dx is square root of 3 over 2 secant squared of theta d theta. That's nice. What happens in the numerator? What is x going to be equal to? If we just bring that 1/2 to the other side. So our numerator should be that's a crazy square root. Square root of 3 over 2 times the tangent of theta minus 1/2. And that will, taking that 1/2 over will give me just x. Did I get everything? Got my denominator, got my dx, and I got my x. Okay, canceling stuff. These secant squareds kindly bow out. We've got to clean up this constant a little bit. So what's that going to be? That's going to be square root of 3 over 2 times the reciprocal of 3/4, which is 4/3. So that gives me 2 square roots of 3 over 3. Oh, which interestingly is 2 over the square root of 3, which helps here, but not there really. So I think what we have now is the integral of 2 over the square root of 3, that's these constants cleaned up, times square root of 3 over 2 tangent of theta minus 1/2 d theta. And it seems like a good idea to distribute that constant through here instead of pulling it out. So what I think I'm at is the integral of the tangent of theta minus 2 over the square root of 3 times 1/2. The 2's cancel. So that looks like a minus 1 over square root of 3. Am I doing all right? And then we can take that. What's the antiderivative for tangent? Natural log of secant, yeah. So it is the natural log of the absolute value of the secant of theta. and then minus 1 over square root of 3 theta. Now we really don't want those thetas hanging around. We got to get rid of them. We have to do reverse substitution. So looking back, and I'm ignoring the plus c for now because we got this, all that other stuff to throw this in with. So let's see. Secant of theta is the square root over square root of 3 over 2. So over here, so that means I really have the natural log of the absolute value of that square root. Now I'm going to write that a little more simply now. Remember, this completed the square version is just our x squared plus x plus 1. It's a little easier to write, so I'm going to go back to that here. So x squared plus x plus 1. But I got to divide by that constant, square root of 3 over 2, to get the secant by itself. Minus 1 over the square root of 3. Now I got to get theta by itself. That one's a little trickier. So here I have the tangent times the square root of 3 over 2. So we're going to have to divide that square root of 3 over 2 to the other side and then take the arctangent. So I think, oops, wrong button. Where do I need to be? Here we go. Theta is equal to the inverse tangent of x plus 1/2 divided by the square root of 3 over 2. And again, double check with my triangle. Wrong button again. Where's my triangle? Right there. Tangent is opposite over adjacent, right? So I want the inverse tangent of that. Oof, now we got to put all this together. If I could keep my pages right, come on. So that right there needs to get combined with all this stuff over here. Oh my. Ooh, I think some nice stuff's going to happen though. All right, so let's see. Let's start putting it together in one screen. So we've got the natural log of the absolute value of, oh, I forgot, what was it? X minus, 8 times x minus 1. There we go. 8 times x minus 1. Then we have this new thing that we just built that's going to go next. So that's that crazy thing there. So plus, let's double check that it is indeed a plus. Yeah, plus. And I mentioned the other day, some of these problems take a lot of paper. The natural log of the absolute value of x squared plus x plus 1 over, is it over the square root of 3 over 2? All right. And then was our next piece, minus a 1/3, or sorry, minus a 1 over square root of 3, tangent inverse of x plus 1 over square root of 3 over 2. X plus 1/2, thank you. And then we have one more piece to go back and grab. Way back here. Then we had a minus 2 over the square root of 3. And I'm struggling to fit this. Get it all. Scoot you over. Oops. 2 over the square root of 3 times the tan inverse of the same thing, right? X plus 1/2, because didn't we complete the square to get that too? Oh crap. You're right. That's the wrong spot. Let's cut you out. Doesn't quite fit, so we will shrink it. Okay, so let's see. We can clean this up a little bit. These two combine. That's going to be, just thinking about those coefficients. Uh-oh, we got to finish up here. That's going to be -3 over the square root of 3. And if you rationalize the denominator, that's negative square root of 3. I don't think there's much I can do with that down there, except rewrite it as a multiple. I think I'm going to leave it where it is. So this right here becomes minus the square root of 3 times the tan inverse of x plus a half over square root of 3 over 2. These guys here we could bring together as a multiple if I bring the 8 in as a power. So keep in mind that I could rewrite that right there as the natural log of the absolute value of x minus 1 to the 8th. Oops. And then the sum of two logs is the log of their product. I'm not sure if that helps us. Do I have my signs right there? Let's double check back here. That was positive and that was positive. And then on this page, no, this page, I think that's right. Oof. Yeah, I don't think that's much better. So I could rewrite all of this here with rules of logarithms as the natural log of the absolute value of x minus 1 to the 8th times x squared plus x plus 1 over that square root of 3 over 2. Do you remember what happens with log of a quotient? It becomes the log of a difference. So technically this right here could be also rewritten as the natural log of the absolute value of x minus 1 to the 8th time. Am I missing a square root? Oh shit. This should be a square root here. Okay. Yep, that should be a square root. Thank you. That should be a square root. All right. So that's the square root of x squared plus x plus 1. And then the log of the quotient here becomes a minus the natural log of the square root of 3 over 2. Now keep in mind, don't we have a plus c hanging out here? So that can be absorbed into the plus c. So some solutions might not even show that at all because it's different by a constant. So we could just get rid of that completely. That could just be absorbed into the constant. In which case we could represent as an antiderivative that combined with, oops, I missed part of it, this here. I don't see a way to clean up the arctangent there. So I think that's about as simple as we can get it. Now there was lots of room for mistake here. We used algebra of completing the square, partial fractions. Oop, there's another class in here. We're gonna have to move out, sorry. So I'll double check this, that we got it right tonight, and then I will get back to you soon just to make sure. We're finishing up section 4. Let me know if you need any passwords to get back into homework. And I will catch you later. Let's save this and then vacate. This is number 15 in the homework. 27. That's why I said feel free to do half of it. If you can complete this one. This is a rough one. Yeah, that's a good point. Automatic A if you can complete it. Yeah. All right, let's